Good afternoon. My name is Ravi Babu, Assistant Professor in Institute of Aeronautical Engineering. Today, I am going to, in first module, that is sample and reconstruction. In that one, I am going to sampling theorem and aliasing. Sampling theorem and aliasing. Now, in previous section, already we see the sampling theorem and reconstruction. So now I am going to illustrate the sampling theorem and frequency in this class, and if not possible to that, if the sampling theorem is not obeyed, what we have to do? Okay, so we are going to sing the sampling theorem and frequency domain, and if the sampling theorem is not obeyed, so what we have to do? That one. So once again, I am going to recalling the sampling theorem. In case of the sampling theorem, the original reconstruction original signal is possible if and only if the sampling frequency at least twice greater than the maximum frequency. Okay, at least twice the maximum frequency. That is, in case of the mathematical formation, f of s equal to 2 into f of m, 2 into f of m, where w of s equal to w of s equal to 2 into 2wm, 2 into 2wm. So that is reconstruction. In case of the sampling theorem, we are going to reconstructing the original signal. Reconstructing the original signal. That original signal is going to be twice of the maximum frequency. Twice of the maximum frequency. Okay. So now in this class, I am going to illustrating the sampling theorem and effect under sampling. And what is the effect under sampling? So what is the effects under sampling I am going to see. So here I am taking the only mathematical expression for the sampling theorem. So that is, if you are to go into making the reconstruction of the that one without loss of information, we have to go into reconstruction. So coming for your mathematical expression, f of s equal to 2 greater than or equal to 2 into fm, where f of s is the angular frequency, and w of s is the f of s is the sampling frequency and w of s is the angular frequency. So fm is the maximum frequency and wm is the angular maximum frequency. Okay, so for that one, if sampling theorem is not obeyed, then what is the main problem for occurring here? It is information is going to be lost. That is nothing but the output of the process. Okay, in case of the block diagram, the output of the process is going to be given to the where it is ADC. Okay, if in ADC block diagram, if sampling process is not completed, that is nothing but quantization process is not going to be assigned the voltage levels. That is, the sampling value is not giving the total exact values. That's why we are going to be lost the information lossing. And coming for the next one, and the signal may be take another frequency also. The signal may be take the another frequency. Why? Because after quantization, if the sampling is not taking the processing at required values, what happened? The frequency level also will be going to be changing. Okay, frequency level also is going to be changing. That's why the sampling theorem is must be obey the system frequencies and domain frequencies. Okay, now in this lesson we are going to see the illustration of the frequency domain, and we will solve one more example problem. Okay, we will solve one more example problem for in sampling theorem. Okay, what happened here? If for example I am going to here sampling effect theorem under sampling. Okay, under sampling. So listen here, it is from 0 to 1. Here the magnitude is, amplitude is 1. Here magnitude, amplitude is 1. Where in case of the sampling, that is W of S is greater than the 2 into W of M. Okay, it is omega sampling theorem. Okay, now, okay. So in this case, what happened here? What is the maximum value here? Analyzing the filter you are using here. Okay, amplifying the filter with 1 by Fs. 1 by Fs here, magnitude value. Okay, that is nothing but after this omega m is going to be greater than this one. Okay, so what is the omega? This is your omega m and it is 2 omega m and it is 2 omega s equal to, okay, omega s. So what I am saying, what is the condition? Omega s greater than the 2 into omega m. That is nothing but it is coming to as here. See this one. There we are getting the gap. This gap. Okay. Here we are getting the gap. When this is in the case of undersampling. Okay. It is in the case of undersampling. Okay. So it is in the case of omega is greater than now. So it is in the case of oversampling. Okay. Oversampling. That is the first case is oversampling. Because of that one, here we are getting the gap. This gap. Okay. Now I am going to for omega s equal to 2 into omega m. Omega s equal to 2 into omega m. That is nothing but sampling frequency, sampling angular frequency is equal to the maximum of 2 times of the maximum of angular frequency. That is, it is equal to sampling theorem statement. It is equal to sampling theorem statement. That's why here it will be copied here. It is, that's why, see this one here, continuously, it is original value. Okay, it is original 1 by f of s, 1 by f of s. Okay, after that one, it is continuously coming. It is continuously coming. That's why it is going to be accept the sampling theorem process. Okay, that is nothing but in this case, quantizer, encoder, and output of the encoder is coming to exact values, and magnitude and frequency is going to be same values. Okay, in this case. Okay, whereas this one here gap is coming now after greater than the sampling frequency is greater than 2 into omega maximum value. That's why we are getting a 1 by f of s. 1 by f of s. Application will be coming. Okay, next coming for the undersampling. Undersampling, that is in case of the case 3. In case of the case 3, so omega s equal to sampling angular frequency is equal to less than the 2 omega m. Less than the 2 omega m. That is nothing but here it will be going to be started before the one completion of the cycle. Before the one completion of cycle. That is in this one. This is okay. How the signal is coming? For example, if you take here reverse like this, it is coming. So it is coming like this. So like this. This one upside triangular against geo order, triangular, same like this. So this is the errors. Okay, under sampling conditions. Okay, under sampling condition it is overlapping. Okay, so it is the under case 3 is going to be shows the under sampling. So this is called as a aliasing. This is called as a aliasing. Only in case of undersampling, we are going to making the aliasing cases. Aliasing cases. That is nothing but this one. These are the aliasing cases. This part, okay, and this part are the aliasing cases. Aliasing cases. Okay. Now, that is here x of t is the signal in spectrum. Okay, x of j omega is the Fourier transformer and it is sampling to sampling frequency f of s to get the discrete time signal x of t, that is spectrum, that is discrete time Fourier transformer. Okay, what I am saying is finally already we know, already in previous classes we see x of t is the sampling input signal, x of t is the input signal. I am going to this one into its samples. Okay, is samples. For example, if you take, okay, I of t, that is nothing but current across at particular times, with particular times. I of t with this, with the time, with respect to time, the signal is, analog signal is like coming like this. Okay, this one is input. X of t is nothing but I am taking the current input. After that one, I am going to sampling. That is, this is one sampling. Already previous classes I am explained. This is sample wise. The waveform is going to be converted. Okay, so X of t is coming to sampling process. After that one, what happened? Quantizer. Quantizer is going to be taking the voltage levels. Okay, when it is going to be taking the voltage levels, that is, it is converted into, it is given to the encoder. That is, that the encoder is given the digital form. That is nothing but it is coming to as voltage levels like this. If equal to voltage levels, so what happened? It is coming to like this. Like this, it is coming. Okay, this is voltage level like this equal. So it is coming like this. So this is one quantizer output value, voltage levels. This one is converted into some encoder. It is going to be digital form 001, 010 like this. Okay, that is nothing but discrete time signal. So what happened to that one? This is going to be coming to as k into t. That's why I am mentioning here x of t is going to be converted as k into x of t. Okay. So first of all, at the place of t, I am taking the j omega. That is nothing but I am taking the Fourier transformer of this one sample signal. I am going to the Fourier transform of the sample signal is converted into discrete time Fourier transformer here. Okay. So now what I am saying is the input signal x of t. Is going to be is in the form of Fourier transformer. Okay, in the form of Fourier transformer, and it will be sampled with sampler frequency f of s, to get the time signal. Okay, which time of the signal? That is x of t, to get the x of t, that is this one, to get the x of kt with spectrum x of j omega. Spectrum nothing but it converted into omega formation. Okay, that is nothing but finally I am going to convert that one into discrete time Fourier transformer. Okay, so this is the process where we are going to sampling theorem and analyzing this one. Okay, now we know that the derivative Fourier transformer is a periodic function in nature. So here we will going to taking the periodic function with sampling frequency. Okay, so what is that one? This is discrete time Fourier transformer now. This discrete time Fourier transformer now I am taking it is a periodic in nature. That is, what is that one? X of kt. Okay, x of kt or x of j omega. This is discrete time Fourier transform. It is in periodic in nature. So this periodic in nature is going to be given the sampling frequencies or angular frequencies. And now we are going to be illustrate this in the form of angular frequencies. Okay, illustration in the form of only angular frequencies. Okay, so here the periodic is going to be converted into only in the form of angular frequencies. Actually, the discrete Fourier transformer is going to be having the illustration of the periodic sample fs and omega s. But we are going to illustrating the only angular frequency only. Angular frequencies. Okay, that is nothing but omega s. Okay, that is nothing but omega s. Now, here x of t is having the spectrum now, that is x of j omega. See this one, x of j omega spectrum, that is Fourier transform. Okay, Fourier transform. Okay, x of t, where is that one? X of t is the input of the ADC. Remember that one. X of t is the input of ADC. It is coming from sampler. Sorry, it is coming from process. Okay, it is coming from process to feedback. From feedback we are getting the x of t. Okay, x of t is nothing but it is a spectrum x of j omega, and here we are using low pass filter. Okay, it is also will be spectrum. Okay, so finally what I am saying, for discrete that one, sampling it, omega s is greater than 2 into omega m. So now I am going to one problem here, that is, take this one. In case of sampling and aliasing problem, convert the continuous time signals cos of 20 into pi t plus cos of 100 into pi t with the sampling frequencies 200 Hz, 100 Hz, 70 Hz. Okay, coming for here, what is in the problem? What they given? The given is that continuous time signal x of t they given. I want to convert this one into with sampling frequencies and also in reconstruct the signal. Okay, that is the thing. But by using these frequencies, I am replacing these frequencies. First of all, see that one. Here continuous time signal is having the two variables. That is 20 into pi t, and that is cos into 100 pi t. Okay. Now I am taking the sampling frequencies 200 Hz, 100 Hz, 70 Hz. That is nothing but 200 is nothing but what? Compare this one to here frequencies. Here omega pi t, cos 2 pi omega t, no? Omega 2 pi f into t, cos omega t. Compare this one, what is omega value? 20 pi. Okay, 20 value. Here 100 value. So whatever this one, this is your in the sampling process frequency matching. Whatever this one 200 is nothing but over damping. Over sampling, over damping. Here 70 is under sampling. Already I have explained now in the diagram. It is under sampling. Okay, see this one. Under sampling case 3. Omega is less than 2 Vm. Okay, 2 Wm. Okay, so 100 is in sampling, 200 is over sampling, it is under sampling. Now we are going to be with this sampling frequencies, we are going to be reconstructing the signal. Okay, and continuous. Okay, go for it. Coming for here, x of t equal to 200 pi t plus 100 cos 100 pi t. Okay, x of t equal to what is that one? Cos 20 pi t plus cos 100 pi t. This is your continuous time signal. Okay. Here x of t containing the two frequency components, that is 20 pi t and 100 pi t. Okay, that is nothing but half of that one frequencies. Okay, that is 100k edges and 50 edges. It is coming to half of this one values. 1 by f, no, f m by 2 we have to take. Okay, 150 edges. Now I am going to first case for sampling theorem. F of s equal to okay, greater than 100 Hz. Okay, it is what is the formula generally? F of s greater than 2 into f of m. What is the maximum frequency here? This maximum frequency is 100. That maximum frequency is 100. That's why I am taking for this one. As per sampling theorem, f of s is greater than 100 Hz. Okay. What they are question asking? if sampling frequency with different frequency edges, that is 200, 170. So here I am taking f of s is, first case is 200 edges. First case is 200 edges. Okay. First I am taking the first case is 200. That is nothing but up to here first case. Okay. Up to here first case. Okay. 200, 170. Which is here second case. Okay. Now coming further. Actually the problem is we are having the continuous time signal x of t equal to cos 20 x of t equal to cos 20 pi t plus cos 100 pi t. Now this is having the two frequencies, that is for 20 10 for 100 50 completed. As per the sampling theorem process, as per the sampling theorem definition, sampling frequency is greater than or equal to the twice of the maximum frequency. Twice of the maximum frequency. Okay, twice of the maximum frequency. So it is nothing but what is the maximum frequency here in the problem? In the problem, the continuous time signal, the frequency is one is the 20, another is the 100. In that one, what is the maximum? 100. That's why I am taking is for sampling theorem f of s is greater than 100 edges. 100 edges. Coming for case 1. This is case 1. Okay. Coming for here case 1. Okay. F of s equal to 200 edges. First case. So what about the t? T equal to 1 by f of s now? Time period equal to 1 by f. 200. Okay. This and also the question is, and also reconstruct the signal. The continuous signal limit we are going to be making the reconstructing. Okay. For that one, I am making the discretizing, that is put t equal to kt. T equal to kt. Okay. What happened? Once again I am writing equation x of k equal to x of t. X of t equal to cos 20 pi t plus cos 100 pi t. Okay, cos 100 pi t. Take this one. At the time of t, I am taking the k continuous to discrete form. Okay, x of k cos 20 pi. What is the t? T equal to 1 by 200. T equal to what is the t? 1 by 200 no? 1 by 200 like this. Okay, t equal to kt. Replace here t equal to kt. Okay, what is the k value? K value is like this. What is the t value? T is nothing but 1 by 200. 1 by 200. See, I am writing here x of k equal to cos 20 pi in t place put here kt. Okay, I am taking first case equal to plus this second case only. Okay, so what happened here? Cos 20 pi. Okay, what is the t value? Here t value is by 200 no? 1 by 200 no? So here I am putting 1 by 200. 1 by 200. So it is capital T. Sorry, it is capital T. We are looking now t equal to capital T. When coming to discrete time. Okay. Similarly for second part also. That is cos 20 pi k by 200. Next cos 100 into pi into k by how much value? 200. So it is coming to as cos this one cancel. So k into pi by 10 plus cos 1 by 2 into k into pi by 2. Okay. Now I am going for reconstruction. Reconstruction nothing but I am putting here k equal to whatever k equal to t by t, no? K equal to t by t. Okay. What is the t value here? T value is nothing but 1 by 200. That is nothing but it is coming to k equal to 200 t. Okay. So that is nothing but k from here k equal to t by t. What is the t value? T by 1 by 200. That equal to 200 t. 200 t. Okay. Take this one. This 200 t, that is nothing but it is, I am taking here y of t. Y of t is nothing but output. Okay. Output of the ADC. Okay. After sampling process, output of the ADC. Okay. Output. Okay. Otherwise, if you take x of t also. Okay. So see this one. Y of t. Sorry. Otherwise, y of k also. No problem. Y of k also. But output section, generally we use the notation of y. Okay. Y of k or y of t. Okay. So y of t equal to cos. What happened? What is the value is here? This one now. Where k is there, we have to replace it to 200 t. So pi by 10 into 200 t plus cos. K is there. So I am going to first of all taking the pi by t here, and what is the k value? K value is 200 t. Okay. After that one, we have to cancel this one. What happened? That one cos 20 pi t plus cos 100 pi t is coming. That is equal to x of t, no? X of t, no? That is, it is in the case of how much value frequency? 200. 200 nothing but what? O damping. Okay. It is in the case of O damping. Okay. It is in the case of O damping. Okay. So what happened to O damping? Omega is equal to greater than or equal to 2 omega m. 2 omega m, no? That's why it is coming to x of t. Next for taking the f of s equal to 100 h. In this case, t equal to 1 by 100. T equal to 1 by 100. So what happened this one? X of k equal to cos 20 pi. Take this equation, same, similarly, next case. Okay. Cos 20 pi. What is the t? T is nothing but kt. Okay. K. What is the k? What is the k is there? What is the capital T? Capital is nothing but 1 by 100. 1 by 100. Capital T is nothing but 1 by 100. Okay. 1 by 100. Plus cos 100 pi. What is the t? T is nothing but kt. Okay. So k into what is the t? Capital T? Capital is nothing but 100. K by 100. Okay. K by 100. So what happened this one? Cos k by 5 to 20 is 5 ja k pi by 5 plus cos k pi. Okay. Now same process. Reconstruct that one. This is your path. This is your signal x of t. Reconstruct that one. In case of the reconstruction, what is the k value? K equal to t by t, no? T by t. So what is that one? 100 t. Okay. Substitute this one into here. K value. Okay. So what happened? 100 into t plus pi 100 into t. So it is coming to as cos 20 by t plus cos 100 by t. It is equal to this one, no? It is equal to this one, no? It is equal to this one. Okay. That is in case of the sampling theory is obeying, sorry, accepting. In that case also, it is coming to x of t. X of t. Okay. Now, I am going for third case. What is the third case? 70 edges. So, first of all, cos 20 pi. I am repeating. Main formula I am pressing here. X of t equal to cos 20 pi t plus cos 100 pi t. First, replace here for this one 70 edges, no? So x of k equal to cos 20 pi. What is the t? T nothing but kt. K. What is the K? Capital T. What is the capital T? 1 by given frequency, no, f of s 70 plus cos, similar also, cos 100 pi k by how much value T, capital T value 70. Okay, this is coming as like this, cos 2 pi by k into it. Again reconstructed this one. Okay, but you see, I am making this equation mathematical, some mathematical, that is here cos 2 pi by 4 into k by pi is same, whereas 10 pi by this one 10 pi by k by 7, 10 pi by k by 7 I am taking as like this. It is coming to same, no? 7 to the 14, k pi minus 4 k pi by 7, that is nothing but 10 pi kt by kt, 7. Same, no? It is coming to same, no? That's why I am splitting like this. Why nothing but see what happened this one. So I am splitting this one like this. After that one, see cos 2 pi by t. So what happened this one? This is going to be cos 2 pi minus k by t. So it is going to be neglected. Okay. So when I am going to for reconstruction part, when I am going for, why? Because cos pi minus theta. Okay, cos pi minus theta nothing but what? Cos theta. Okay, cos 2 pi minus theta formula, mathematical formula. Cos 2 pi minus theta. Okay, that is nothing but cos theta. This is coming to like this. Okay, so for reconstruction, what is the formula for reconstruction? Replacing of k equal to t by t, k, no? K equal to t by capital T, no? So for that one, what is the capital T here? T equal to 70. Capital T equal to 1 by 70. Replace that one, 70 T. Okay. So this 70 T, you are going to be replacing this 70 T into in our equation. So what happened? 2 pi by 70 T plus 4 pi by 70 T. So what happened this one? Cos 20 pi by T plus cos 40 T. Where it is same as this one? No. No. Okay. That is nothing but when it is in the under damping condition. Under damping condition. This is the way we are going to be making the signals as sampling. Signals, sampling the signals and reconstructing the sampling signals. Okay, reconstruction the sampling signals. Okay, now reconstruction the sampling signals. Okay, now I am going to what is the practical acceptation selection of the sampling theorem. Okay, why we are going to practically we are going to selecting the sampling rate, that is information loss due to the sampling. Okay, when it is going, if it is going to accept the sampling theorem statement, that is f of s is greater than or equal to 2fm. Okay, that's why if it is not obeying this one, the information is going to be losses. The information is going to be losses. Okay, see this one diagram. I will explain this one. This information is lossing. Okay, here some lossing, but what about here? Continuously coming. Continuously coming. This is our first. Next, information losses due to the disturbances. Okay, already you saw in the control system. Similarly, disturbances is occurring at the place of plant or process, or before the plant or process. Otherwise, in case of the controller also. In case of the controller also. That's why information is going to be lost of the disturbances. Okay, if you not given the proper the sampling processing. Okay, sampling processing. And next one is distribution of effects and final word length effects algorithm equivalence. Already I explained this one into in the case of the what is the use of the digital control system in explanation. Finite word length. Okay, if it is not a finite word length, so the mismatching of the ADC and DAC bits levels. Okay, and coming for the algorithm requirement, if the algorithm computer is not generating the accurate values, so it is going to be effect on the DSC. Okay, it is affected on the DSC programming output effect. So the plant is going to be not properly planned. Okay, this is your sampling theorem and aliasing part. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.